Morning, folks. How are we doing? Questions while we wait a few moments? Everybody comes in? Here, Matthew, here's what I'm going to suggest your mistake is. You might be treating it as 8x all to the power ln x, when in fact it's only the x that's to the power ln x. This is the typical mistake students make with that question. Today, we're going to see implications of the derivative. See what the derivative tells us about the shape of the graph. And let's start with an observation. Observe that if, well, so first of all, let's not start with an observation, but rather start with a definition. A function f of x is said to be increasing if, whenever x1 is less than or equal to x2, then f of x1 is less than or equal to f of x2. And we can say strictly increasing if the inequalities, if this is replaced by and decreasing similarly. Right, and I mean, you know what this means. If we look at the function x squared, you know the graph of x squared. And if you take two numbers that are bigger than 0, then a squared is going to be less than b squared, right? Your function is an increasing 1. Right, from the graph, if you take two values, they get larger and larger. If one value is bigger than the other, then so will their image. Of course, it works the other way around, right? For values less than 0. If you take two values here, this one is going to be the larger one versus that one. So your function is actually decreasing from negative infinity to 0. Observe that if the derivative of a function is bigger than 0, well, you know the derivative. You know the derivative is a limit as h goes to 0. So if this is bigger than 0, that means that for values of h close to 0, so thus if h is close to 0, then this whole expression has to be positive, right? It's the, well, bigger than or equal to. Well, actually bigger than is fine too. Right? If this limit exists and it's something bigger than 0, then eventually this has to be bigger than 0 as well. Right? Because the limit is the behavior of the function. So if h is bigger than 0, then multiply this whole inequality by h. H being bigger than 0, the inequality remains. The inequality is preserved, and we get f of x plus h minus f of x is bigger than 0. In other words, f of x plus h is bigger than f. Your function is strictly increasing, right? If h is bigger than 0, what we're saying is, if you take an x, and then something bigger than 0, so x plus h is going to be bigger than x, and your function is getting larger. Similarly, if h was less than 0 in here, and you multiply by h, if you multiply this whole thing by h being negative, the inequality reverses, and we get f of x plus h minus f of x is less than 0. And bring that over, and we get f of x plus h is less than f of x. But h is less than 0, so this would be less than x. Right? So, and this value would be less than that value. So it would still be increasing. In either case, your function is increasing. What are we saying? If the derivative is positive, then f is increasing. You can repeat the whole argument. If the related rates, there's not much to explain. It's difficult. It's difficult and there's no way around it. As the word suggests, it's rates that are related, so you need to find a relationship. There's nothing else you can do. The more you do, the easier they become, but there's nothing I can say that'll make it any easier. If the derivative is less than 0, you can do the same argument. I'm going to let you repeat. If the derivative is less than 0, then f of x is decreasing. Again, convince yourselves, but it's the same argument. Let's take a few examples from the book. The question is asking us to find intervals on which f is increasing and decreasing. And while we're there, find local max and min. All right. So you see the whole point, right? If the derivative is continuous, then in order to go from something positive to something negative by the intermediate value theorem, it has to be 0 somewhere. So if we have a derivative, the critical points will play an important role in determining where the function is increasing and where it's decreasing. In between critical points, the function has to behave always in the same way. Let's illustrate. We have this function. Let's find the critical points. First of all, you recognize this as a polynomial. So very well behaved, continuous everywhere, differentiable everywhere. Its derivative is again a polynomial, which will be continuous and differentiable and so on. Derivative 3x squared minus 12x minus 135. And we factor out a 3 here. In fact, I think this is the example I had given you last time, right, where we were asked to find critical points. Here we're asked for a bit more. How does this factor? This factors as x minus 9, x plus 5. Is that correct? Looking good. And what are the critical points? Everyone? Critical points? You know what they are. Thank you. 9 and minus 5. So now what I like to do is something called a first derivative chart, where I will label the critical points in increasing order. So in this case, negative 5 and 9. Normally inside your domain, but of course in this case, the domain is all real numbers, so there's no issue. And now the point is that for values less than negative 5, critical points could be points coming from the denominator, Morgan, as you know. Absolutely right. Critical points are where the derivative is 0 or the derivative does not exist. So the derivative would not exist if the denominator was 0. Of course, you want to be careful because by definition, critical points are in the domain. So in some cases where the derivative, where the denominator is 0, would not be in the domain, but sometimes it is. So you have to be careful. However, in a first derivative chart, whether it was a critical point or a point not in the domain, this would have to be included. And what I want to point out, right, I mean, this function is a continuous function. And it's 0 only at these two values. So for values less than negative 5, the derivative is either always positive or always negative. It does not change signs. Because if it changed signs by the intermediate value theorem, it would have to be 0 somewhere, and it isn't. Right? For values less than negative 5, your function is never 0. And by function, I mean the derivative. The derivative is never 0, so it cannot change signs. It must be either always positive or always negative. So take any point less than negative 5. You can take any point you want, negative 6, negative 10, whatever, and plug it into the derivative. If we plug in negative 10, this is negative 19. Negative 10 plus 5 is negative 5. Negative times negative is positive. Times positive, the whole thing is positive. Your derivative is always positive from negative infinity to negative 5. What does that mean as far as the function is concerned? If the function is positive, if the derivative is positive, your function is increasing. So that means that your function is increasing in this interval. Now, repeat on the interval negative 5 to 9. Take any point between negative 5 and 9, in particular 0. If you plug in 0, the derivative is negative 135. In other words, negative, which means your function is decreasing. Finally, take a number bigger than 9 something bigger than 9 minus 9 is positive. Something bigger than 9 plus 5 is positive. So positive, positive, positive. The product is positive, which means your function is increasing. Maxwell brings up an interesting question. So, do we have an absolute max at -5? Well, let's think about what can happen here. Can we draw a function which is increasing and then decreasing and then increasing again? One thing's for certain, we certainly have a local maximum occurring at 5, right? Your function is going to be increasing and then decreasing. We cannot conclude absolute because we don't know how large the function gets after 9. It might be absolute, it might not. At this stage, we don't have enough information. But we certainly can conclude local max here. And similarly, at 9, right, your function is decreasing to the left and then increasing afterwards. So we certainly have a local minimum occurring there. We don't know about absolute because it's not clear what is happening for large values, right? I mean, take this example. Your function could look something like this, where this is less than that, so it could be absolute, or your function could look something like this, where it gets much smaller than it was here. So this first derivative chart does not give us enough information to conclude absolute max or min in this case. But we can certainly conclude local minimum for now. And there it is. We have given intervals where the function is increasing from -infinity to -5 and from 9 to infinity. And an interval where the function is decreasing from -5 to 9, labeling local max and min as well. Let's try another one. All right. Maybe a first question. What is the domain here? Somebody wants an example with a lot of variables. We can perhaps do that. Domain is all real numbers. Exactly. Let's take the derivative. Whatever you want to do, right? You could expand first and then differentiate term by term. Or you can do the Product rule. Why don't we expand? This is really x to the 5 over 3 minus 3x to the 2/3. I think it's going to be easier, right? 5 over 3 x to the 2/3 minus 2x to the minus 1/3. I don't know. I think I'm going to make the final exam different. We'll see. Let's wait until everything is marked. Then we'll discuss it. Let's factor out some stuff. What can we factor out? Yeah, I think I'll write the final. I'm sure it went extremely well. I haven't looked at the marks yet. No, we're far from knowing anything. We're not done marking. It's going to be a while. Let's factor out a 1/3 x to the negative 1/3. Look, it depends how much the questions were worth. If the question was worth 1 mark, don't expect too many part marks. I think it's either going to be right or wrong. If the question was worth 4, then you could expect some part marks. Yeah, it's going to be very long to mark. So let's factor out a 1/3 x to the negative 1/3. What does that leave us with? 5x minus 6. Is that correct? (5x minus 6). So, well, I mean, if you want to take it a step further, does everybody have this? Questions? What are the critical points? Zero and 5 over, and what is it? 6 over 5, thank you. 0 and 6 over 5, right? It's all good. So let's do a first derivative chart. Labeling these points. And now take a value less than 0. If you take something less than 0, this is going to be negative. Minus 6 is negative. Cube root of a negative number is negative. So negative over negative, the whole thing is positive. Keep in mind that these questions are typical for a final exam, and you don't have a calculator in normal circumstances. So this argument is an important one to be able to make, right? Of course, you can just plug in a negative number and work it out. But this nice argument is important. Function is, the derivative is positive, so your function is increasing. If you take a number close to 0, right, because now, well, I mean, of course, 1 is in that interval, but whatever you want to do. The argument I like to make is if you take something close to 0 but larger than 0, right, this is going to be close to 0, so the numerator is going to be close to negative 6. A number bigger than 0, if you take a cube root, it's still bigger than 0. So negative on top positive on the bottom. The whole thing is negative. Don't make the mistake, right? You're looking at this and you're telling yourself, well, if I know how it starts, then it always alternates, right? And that seems to be the case here as well. The derivative is negative, so your function is decreasing. And if you take a very large number, you can take anything you want here, right? Very large. This is going to be very large. -6 is still very large, so positive here. Cube root of a large positive number is still positive, so the whole thing is positive. Again, seems to alternate positive, negative, positive. Don't make that assumption. It's not always true. And you need to test. Absolutely. Then there are examples where a function is increasing, so plus plus, before and after a critical point. Let's go back to this. What is happening at 0? Your function is increasing and then decreasing. You see what happens, right? We have a local maximum occurring at 0. And over here, your function is decreasing and then increasing. You see what happens? You have a local minimum occurring there. Shall we do one more? And then we'll move on. All right. Consider this. Same question, we're looking for, so domain here, what is the domain? Right? Here, this is a polynomial, so you know you can plug anything in that you want. Domain is all real numbers for this part. This is an exponential, and you know that's defined everywhere as well. So the domain is all real numbers. Absolutely. Let's take the derivative. What is the derivative? 4x cubed e to the minus x plus x to the 4 e to the minus x times -1, right? It's a product rule. The function is the product, so product rule applies. There it is. Is x allowed to be 0 in this example? Or in the previous one? In number 12? Here you don't have a negative exponent. So it's not 1 over 0. You're fine. Cube root of 0 is 0. 0 squared is 0. You can plug in 0 into this. It's all good. You can also plug in negative numbers, right? Because of the cube root. So all real numbers. But the derivative, exactly, the derivative is not allowed to be 0. When x is 0, the derivative does not exist. That's why 0 is a critical point. It's in the domain, and it's a point where the derivative does not exist. We have this. Yeah, Matthew, we'll do one after this. Somehow. So what are we doing? We're looking for critical points. Points where the derivative is 0 or the derivative does not exist. Let's factor out. What are we going to factor out? X cubed e to the minus x. Leaving us with 4 minus x. You see that every term here is a polynomial or an exponential. The derivative exists everywhere. So critical points are going to be where the derivative is equal to 0. I think we can just read them off. What are the critical points? Where did the minus 1 come from? Liam, you tell me. Chain rule, right? The derivative of the exponential is the exponential, and then you differentiate the inside. Derivative of negative x is negative 1. Critical points are 0 and 4. Thank you, everyone. And now let's draw a first derivative chart. Let's draw a first derivative chart. Labeling your critical points, 0 and 4. Now take a number less than 0. Yep, these derivative charts, very nice to work with, and they tell you all the information you need to know. Take a number less than 0 and plug it in. Where are we plugging it in? To the derivative. So if you take a number less than 0 and you cube it, you get a number less than 0. The exponential is always positive, so we don't need to worry about that. And 4 minus a number less than 0, 4 minus a negative, minus minus gives you plus. So this is positive, that is negative. The product is negative. So your function is decreasing. Take 1. 1 cubed is 1. 4 minus 1 is 3. This is positive, that's positive. This one is always positive. So your function is increasing. And finally, if you plug in 5, it's going to be positive, positive. 4 minus 5 is negative. There it is. What is happening at 0? Right, your function is decreasing and then increases. You see what's happening. At 0, we have a local minimum. We're going to do concavity right after this. We're going to do an example where you've got other variables, A and B, but then we'll move on to the concavity. At 4, your function is increasing and then decreases. You see what's happening here? Local max. Can we adapt this? To A's and B's? Morgan. Which one? This one here? This, I mean, just plug in any number bigger than 4. Plug in 5. 5 cubed is the less than 0. Well, again, take -1. -1 cubed is -1. The exponential is always positive, so we can always forget about it. And 4 minus -1, or 4 plus 1 is 5. So negative, positive, positive, the whole thing is negative. Let's say we had values of A and B. And let's say A is strictly bigger than 0, B can be anything. Find the critical points. Well, in fact, find intervals of increase and decrease, blah, blah, blah. So derivative, you know what to do. It's a product, right? So product rule applies. Differentiate the first one, leaving the second one fixed. Plus, leave the first one fixed. Differentiate the second one. Oh, yeah, you see. Now we're in trouble. Instead of a plus here, let me change it. Where A is that and B is not. Well, let's not put any conditions on B. Tempting, but I mean that's the thing, right? I mean, when you ask me for, if you want me to come up with something on the spot involving variables, doesn't always work out immediately. Right, so there we go. So let's change it to that. Or if you prefer, this is b to the 4, x to the 4, e to the minus ax. Well, again, there are no guarantees that this is going to work. Let's just hope it does. Look, I mean, I realize that it's slightly tricky, but don't, what can I say? Don't let that throw you off. If you can do this, you can do that. It's exactly the same thing. Keep in mind that A and B are just numbers. So if we rewrite it this way, this is just a constant, b to the 4. So we can leave it out. Differentiate this is a product. So product rule applies. 4x cubed, e to the minus ax. Plus x to the 4, derivative of the exponential, is this. You can leave it in and treat it as a chain rule, Rachel, absolutely. It's up to you. That's fine too. And now let's factor out In exactly the same way we did here, let's factor out an x cubed e to the ax. So b to the 4 x cubed e to the minus ax. What are we left with? This has been factored out. We have a 4. That's gone. X cubed is gone, so we have an x and a minus a. There it is. So observe that this exists for all values of x. So critical points are where this is going to be equal to 0. So what do we have? We have a product equal to 0. And this happens. Somebody want to address that? Shamir, what other half? There it is. So we have a product equal to 0. And when is a product equal to 0? When at least one of the factors is 0. So x equals 0 from here. This exponential is never 0. Here, as Zoe points out, we have a product, we have a critical point 4 over a. We can divide by a because it's not equal to 0. And lastly, let's address the b. Because no condition is given on b. So it actually is possible that b is equal to 0. And what happens in that case? If b is equal to 0, your function is always 0. So all points would be critical points here. Not an interesting case, but still something that should be addressed for completeness. So if b is not 0, these are your critical points. Well, a doesn't have to be bigger than 0. In fact, all a has to be is not equal to 0. And in fact, if here I'm saying, suppose a condition was given that a was bigger than 0. If no condition was given, then you would have to check some cases. This would be fine as long as a is not 0, right? Because you don't want to divide by 0. And then you would go back and ask the question, what happens if a is equal to 0? Well, if a is equal to 0, you don't have an exponential. So you just have bx to the 4. b to the 4x to the 4. Where your only critical point would be x equal to 0 in that case. So what should you consider when dealing with many variables? First, don't worry about it. Treat it as if these were just numbers. Find the derivative. Simplify. Right? Because the question was asking in this case for critical points. So take the derivative normally, simplify, and then ask, what are the critical points? Well, here critical points are when this is equal to 0. So when is a product equal to 0? If one of the factors is 0, and then you go from there. All right, so exactly the same steps as here, except that you have the added slight difficulty of working with unknown values A and B. And once you have an answer, right, as in this case, nothing is stopping you from convincing yourselves by taking values of A and B, right? If you're getting this as the answer, go back and say, let A be 2 and B be 3. And repeat the question in that case. See if your answers coincide. So Zoe is asking us to do a first derivative chart for this. Let's do it. Right, so first of all, you understand that if b is 0, your entire function is 0. So we're not going to discuss that because there's nothing. I mean, on an exam, you'd probably want to write a sentence saying if b is 0, the function is entirely 0 and nothing interesting comes out of that. So we'll take b to be non-zero. And let's draw a first derivative chart. Well, you cannot choose values for A and B. That's not what I'm saying. What I'm saying is once you have an answer, you can convince yourselves that it's right by choosing values of A and B and redoing this question in that situation. Shamir, in this case, if you were not told that it was bigger than 0, then you absolutely would have to do 2 charts, right? Because your critical point would still be 4 over A. But if A is positive, this is going to be positive, and if A is negative, it's going to be negative. So you really need 2 charts to determine where to position your 4 over A. In this case, though, if we are still assuming A to be bigger than 0, we have 2 critical points, 0 and 4 over A, and we know that to be positive. Well, Zoe, the original question said for A bigger than 0, so there's no ambiguity. If that wasn't there, though, if A could have been positive or negative, then 2 charts would have been important. But here, no issue. All right. So, take any number less than 0. Right? I mean, it seems that you should be worried about that, but there's no need to be. Let's see what happens. If you plug in -1, this is positive, something to the 4. -1 cubed is -1. The exponential is always positive, so you can forget about that. And if you're plugging in -1 for x, then this becomes 4 plus A. A is positive, so 4 plus A is positive as well. It's actually bigger than 4. So positive, negative, positive, positive. The whole thing is negative. Your function is decreasing. Well, now becomes the worrisome part. You don't know what A is. So how can you choose a number in here? Might be your question. Well, that, Michael is suggesting 4, but what if A is 4? If A is 4, this is actually 1. And 4 is not going to be in this interval. But, and the larger A gets, the smaller A over 4 gets. Exactly that. Right? There are ways around it. Well, exactly, Matt. My suggestion is to just do a little bit bigger than 0. Not an actual number, but an argument. First of all, this is always positive, so you can forget that. The exponential is always positive, so you can forget that. If you take a number very close to 0, but bigger than 0, and very nice, Michael, that was my next suggestion. You could actually take the number 2 over A, and it has to be in here. It's actually the midpoint. So that's very nice. If you absolutely want to plug in a number, you can find one. 2 over A works. But you don't need to. Take a number very close to 0. Not an actual number, but more of an argument. A number close to 0, but bigger than 0. When you cube it, you get something positive. If you take a number very close to 0, this is going to be close to 0. As close as you want it to be to 0. 4 minus a number close to 0 is going to be close to 4. So positive here, positive there, the whole thing is positive. So your function is increased. Finally, take a number bigger than 4 over A. Again, an argument is easier to do, but as Michael suggests, and Kamal, 8 over A or 5 over A, these are 2 possibilities of points you can plug in. But I'm going to make an argument similar to that near 0. I'm going to take a number as large as I want. Very, very large. Large positive number cubed is positive. If x is a large positive number, since a is positive, this is going to be a large positive number. As large as you want it to be. 4 minus a large number is going to be negative. So positive, 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 negative, the whole thing is negative. There it is. All I'm suggesting, don't let these other variables worry you should they come up on the final. They're just constants. If you can do the question with those as actual numbers, 6 and 7, then you can do it with A and B. If you're comfortable with the material, there's no reason for you not to be able to do this. And I mean, you understand why we threw those in, right? Because of websites like Wolfram Alpha and Mathematica and stuff like that. right? These websites where you can just plug in and they will give you the critical points and the derivative and this and that. Well, I mean, how do I suggest you prepare? Lots and lots of exercises. I understand that with these variables, you really don't have that many, but it doesn't matter. If you can do the questions without the variables, you can do them with. That's all I'm saying. Just be very comfortable with the material, and you're good to go. All right. Perhaps a good place for us to end then. I was going to do, we were going to look at the second derivative, but we'll do that on Wednesday. Questions in the meantime? Anybody? Thank you all for coming. And we will pick this up again on Wednesday. You guys have a good one. I'll see you then.